Of lectures, we get our networking basics right. We look at basic networking concepts like switching, routing, gateways, etc. We then understand DNS, and then we get a basic introduction to core DNS. We look at how to configure DNS settings on a Linux system. We then understand basics of network namespaces in Linux. Again, I'm not going to bore you with theories on OSI models or network layers. We're just brushing up enough networking to understand the rest of the section in this course. Now, we don't just go through the concepts, we see how these are configured on our systems, specifically from a Linux perspective. So there are going to be lots of commands. We look at these from a system admin's and the application developer's perspective, and not necessarily from a network engineer's. That way, later on when we discuss these in the context of our course, you know what we are talking about, where to look for information, where things are configured, how to troubleshoot, etc. And of course, as always, if these seem to be too basic for you, if you're already good with networking in Linux, feel free to skip these lectures and go straight to the ones on Kubernetes. So let's get started. So what is a network? We have two computers, A and B, laptops, desktops, VMs on the cloud, wherever. How does system A reach B? We connect them to a switch, and the switch creates a network containing the two systems. To connect them to a switch, we need an interface on each host, physical or virtual, depending on the host. To see the interfaces for the host, we use the ip-link command. In this case, we look at the interface named ETH0 that we will be using to connect to the switch. Let's assume it's a network with the address 192.168.1.0. We then assign the systems with IP addresses on the same network. For this, we use the command ipaddr. Once the links are up and the IP addresses are assigned, the computers can now communicate with each other through the switch. The switch can only enable communication within a network, which means it can receive packets from a host on the network and deliver it to other systems within the same network. Say we have another network containing systems C and D at address 192.168.2.0. The systems have IP address 192.168.2.10 and 2.11 respectively. How does a system in one network reach a system in the other? How does system B with the IP 192.168.1.11 reach system C with the IP 2.10 on the other network? That's where a router comes in. A router helps connect two networks together. It is an intelligent device, so think of it as another server with many network ports. Since it connects to the two separate networks, it gets two IPs assigned, one on each network. In the first network, we assign it an IP address 192.168.1.1, and in the second, we assign it an IP 2.1. Now we have a router connected to the two networks that can enable communication between them. When system B tries to send a packet to system C, how does it know where the router is on the network to send the packet through? The router is just another device on the network. There could be many other such devices. That's where we configure the systems with a gateway or a route. If the network was a room, the gateway is a door to the outside world, to the other networks, or to the internet. The systems need to know where that door is to go through that. To see the existing routing configuration on a system, run the route command. It displays the kernel's routing table. And within that, as you can see, there are no routing configurations as of now. So in this condition, your system B will not be able to reach system C. It can only reach other systems within the same network in the range 192.168.1.0. To configure a gateway on system B to reach the systems on network 2.0, run the iproute add command and specify that you can reach the 192.168.2.0 network through the door or gateway at 192.168.1.1. Running the route command again shows that we have a route added to reach the 192.168.2.0 series network through the router. Now remember, this has to be configured on all the systems. For example, if the system C is to send a packet to system B, then you need to add a route on system C's routing table to access the network at 1.0 through the router configured with the IP address 2.1. Now suppose these systems need access to the internet. Say they need access to Google at 172.217.194.0 network on the internet. So you connect the router to the internet and then add a new route in your routing table to route all traffic to the network 172.217.194 through your router. There are so many different sites on different networks on the internet. Instead of adding a routing table entry for the same router's IP address for each of those networks, you can simply say for any network that you don't know a route to, use this router as the default gateway. This way, any request to any network outside of your existing network goes to this particular router. So in a simple setup like this, all you need is a single routing table entry with the default gateway set to the router's IP address. Remember, instead of the word default, you could also say 0.0.0.0. It means any IP destination. Both of these lines mean the same thing. A 0.0.0.0 entry in the gateway field indicates that you don't need a gateway. For example, in this case for system C, to access any devices in the 192.168.2.0 network, it doesn't need a gateway because it is in its own network. But say you have multiple routers in your network, one for the internet, another for the internal private network, then you will need to have two separate entries for each network. One entry for the internal private network and another entry with the default gateway for all other networks, including public networks. So if you're having issues reaching internet from your systems, this routing table and the default gateway configuration is a good place to start. Let us now look at how we can set up a Linux host as a router. Let's start with a simple setup. I have three hosts A, B, and C. A and B are connected to a network 192.168.1 and B and C to another on 192.168.2. So host B is connected to both the networks using two interfaces 80 and 81. A has IP 192.168.1.5, C has 192.168.2.5, and B has an IP on both the networks 1.6 and 2.6. How do we get A to talk to C? Well, basically, if I try to ping 2.5 from A, it would say network is unreachable. And by now we know why that is. Host A has no idea how to reach a network at 192.168.2. We need to tell host A that the door or gateway to network 2 is through host B. And we do that by adding a routing table entry. We add a route to access network 192.168.2 via the gateway 192.168.1.6. If the packets were to get through to host C will have to send back responses to host A. When host C tries to reach host A at 192.168.1 network, it would face the same issue. So we need to let host C know that it can reach host A through host B, which is acting as a router. So we add a similar entry into host C's routing table. This time we say to reach network 192.168.1.0, talk to host B at 192.168.2.6. When we try to ping now, we no longer get the network unreachable error message. That means our routing entries are right, but we still don't get any response back. By default, in Linux, packets are not forwarded from one interface to the next. For example, packets received on ETH0 on host B are not forwarded to elsewhere through ETH1. This is this way for security reasons. For example, if you had ETH0 connected to your private network and ETH1 to a public network, we don't want anyone from the public network to easily send messages to the private network unless you explicitly allow that. But in this case, since we know that both are private networks and it is safe to enable communication between them, we can allow host B to forward packets from one network to the other. Whether a host can forward packets between interfaces is governed by a setting in this system at file proc sys net IPv4 IP_forward. By default, the value in this file is set to 0, meaning no forward. Set this to 1 and you should see the pings go through. Now remember, simply setting this value does not persist the changes across reboots. For that, you must modify the same value in the etc syscontrol.conf file. So let's take away some key commands from this lecture. These will be handy in the upcoming lectures. IP-link is to list and modify interfaces on the host. IPADDR command is to see the IP addresses assigned to those interfaces. IPADDR add command is used to set IP addresses on the interfaces. Now remember, changes made using these commands are only valid till a restart. If you want to persist these changes, you must set them in the etc network interfaces file. iproute or simply the route command is used to view the routing table, and iproute add command is used to add entries into the routing table. And finally, remember the command to check if IP forwarding is enabled on a host, if you're working with a host configured as a router. Well, that's it for this lecture. In the next lecture, we will discuss about DNS configurations. In this video, we get introduced to DNS in Linux for the absolute beginners. We will discuss the basic concepts and view some commands that will help us explore DNS configuration on hosts, specifically Linux hosts. At the end of this section, you will go through a practice test where you're given a set of challenges related to DNS and are asked to solve them on a live, practical, hands-on lab environment right in your browser. We have two computers, A and B, both part of the same network, and they've been assigned with IP addresses 192.168.1.10 and 1.11. You're able to ping one computer from the other using the other computer's IP address. You know that System B has database services on them, so instead of having to remember the IP address of the System B, you decide to give it a name DB. Going forward, you would like to ping System B using the name DB instead of its IP address. If you try to ping DB now, you would see that host A is unaware of a host named DB. So how do you fix that? Basically, you want to tell System A that System B at IP address 192.168.1.11 has a name DB. You want to tell System A that when I say DB, I mean the IP 192.168.1.11. You can do that by adding an entry into the etc host file on System A. Mention the IP address and the name you want your host to see System B as. We told System A that the IP at 192.168.1.11 is a host named DB. Pings to DB now get sent to the correct IP and are successful. Now there is an important point to note here. We told System A that the IP at 192.168.1.11 is a host named DB. Host A takes that for granted. Whatever we put in the etc host file is the source of truth for host A. But that need not be the truth. Host A does not check to make sure if System B's actual name is DB. For instance, running a host name command on System B reveals that it is named host 2. But host A doesn't care. It goes by what's in the host file. You can even fool System A to believing that System B is Google. Just add an entry into the host file with an IP mapping to www.google.com. Then ping Google and you will get a response from System B. So we have two names pointing to the same system. one as DB and another as Google, and we can use either names to reach system B. You can have as many names as you want for as many servers as you want in the etc host file. Every time we reference another host by its name from host A through a ping command or SSH command or through any of the applications or tools within this system, it looks into its etc host file to find out the IP address of that host. Translating hostname to IP address this way is known as name resolution. Within a small network of few systems, you can easily get away with the entries in the etc host file. On each system, I specify which are the other systems in the environment, and that's how it was done in the past. Until the environment grew and these files got filled with too many entries, and managing these became too hard. If one of the server's IP changed, you would need to modify the entries in all of these hosts, and that's where we decided to move all these entries into a single server who will manage it centrally. We call that our DNS server. And then we point all hosts to look up that server if they need to resolve a host name to an IP address instead of its own etc host files. So how do we do that? How do we point our host to a DNS server? Our DNS server has the IP 192.168.1.100. Every host has a DNS resolution configuration file at etcresolve.conf. You add an entry into it specifying the address of the DNS server. We say name server and point it to 192.168.1.100, and that should be it. Once this is configured on all of your hosts, every time a host comes up across a hostname that it does not know about, it looks it up from the DNS server. If the IP of any of the hosts was to change, simply update the DNS server and all hosts should resolve the new IP address going forward. You no longer need any entries in the etc host file in any of the hosts. But that does not mean you can't have entries in host file. You still can. For example, say you were to provision a test server for your own needs. You don't think others would need to resolve the server by its name, so it need not be added to the DNS server. In that case, you can add an entry into your host's etc host file to resolve this server. You can now resolve the server, however, no other system will be able to do that. So a system is able to use host name to IP mapping from the etc host file locally as well as from a remote DNS server. What if you have an entry in both places, one in your etc host file and another in DNS? I have an entry in my local file set to 192.168.1.115 and someone added an entry for the same host to 192.168.1.116 on the DNS server. In that case, the host first looks in the local etc host file and then looks at the name server. So if it finds the entry in the local etc host file, it uses that. If not, it looks for that host in the DNS server. But that order can be changed. The order is defined by an entry in the file etc/nsswitch.conf. The line with the host's entry. As you can see, the order is first files and then followed by DNS. Files refers to etc host file and DNS refers to the DNS server. So for every host name, the host first looks into the etc host file, and if it cannot find it there, it then looks at the DNS server. This order can be modified by editing this entry in the file. As per this order, our host would resolve the test server to 192.168.1.115. What if you try to ping a server that is not in either list? For example, I try and ping www.facebook.com. I don't have facebook.com in my etc host file and I don't have it in my DNS server either. So in that case, it will fail. You can add another entry into your resolve.conf file to point to a name server that knows Facebook. For example, 8.8.8.8 is a common, well-known public name server available on the internet hosted by Google that knows about all websites on the internet. You can have multiple name servers like this configured on your host, but then you will have to configure that on all your hosts in your network. You already have a name server within your network configured on all the hosts. So in that case, you can configure the DNS server itself to forward any unknown host names to the public name server on the internet. You should now be able to ping external sites such as facebook.com. Until now, we've been just trying to reach systems with their names like web, DB, NFS, etc. But we just tried to ping Facebook at www.facebook.com. What is this name with a www and .com at the end? It's called a domain name, and it is how IPs translate to names that we can remember on the public internet, just like how we did for our hosts. Now, the reason they are in this format, separated by dots, is to group like things together. The last portion of the domain name, the .coms, the .nets, .edu, .org, etc., are the top-level domains. They represent the intent of the website, .com for commercial or general purpose, .net for network, .edu for educational organizations, and .org for non-profit organizations. Let's look at one in particular. In Google's case, the dot is the root. That's where everything starts. .com is the top-level domain. Google is the domain name assigned to Google, and www is a subdomain. The subdomains help in further grouping things together under Google. For example, Google's map service is available at maps.google.com. So maps is a subdomain. Google's storage service is available at drive.google.com. Mobile apps are available at apps.google.com. Google's email service are available at mail.google.com. You can further divide each of these into as many subdomains based on your needs. So you begin to see a tree structure forming. When you try to reach any of these domain names, say apps.google.com, from within your organization, your request first hits your organization's internal DNS server. It doesn't know who apps or Google is, so it forwards your request to the internet. On the internet, the IP address of the server serving apps.google.com may be resolved with the help of multiple DNS servers. A root DNS server looks at your request and points you to a DNS server serving .coms. A .com DNS server looks at your request and forwards you to Google. And Google's DNS server provides you the IP of the server serving the app's applications. In order to speed up all future resolves, your organization's DNS server may choose to cache this IP for a period of time, typically a few seconds up to a few minutes. That way, it doesn't have to go through the whole process again each time. So that was out in the public. What about your organization? Your organization can have a similar structure too. For example, your organization could be called as mycompany.com and have multiple subdomains for each purpose. The www for external facing website, mail.mycompany.com for accessing your organization's mail, Drive for accessing storage, pay.company.com for accessing the payroll application, HR for accessing HR application, etc. All of these are configured in your organization's internal DNS server. The reason we discussed all of this is to understand another entry in the etcresolve.conf file. Remember, this is the file where we configured the DNS server to be used for our host. With that, we were able to resolve servers in your organization with just their names like web. We have now introduced more standard domain names like web.mycompany.com or db.mycompany.com, etc. Now, when you ping web, you can no longer get a response. Of course, this is because we are trying to ping web, but there is no record by the name web on my DNS server. Instead, it is web.mycompany.com, so you have to use web.mycompany.com. Now, I can understand if someone outside our company wants to access our web server, he would have to use web.mycompany.com. But within our company, your own company, you want to simply address the web server by its first name, web, just like how you address other members in your family, simply by their first names, which is not the case when someone outside your family addresses them using their full names. So what do you do to configure web to resolve my web.mycompany.com? You want to say, when I say web, I mean web.mycompany.com. For that, you make an entry into your host's etcresolve.conf file called search and specify the domain name you want to append. Next time you try to ping web, you will see it actually tries web.mycompany.com. Now, your host is intelligent enough to exclude the search domain if you specified a domain in your query like this. You may also provide additional search domains like this. So it would mean when I say web, I mean web.mycompany.com or web.prod.mycompany.com. So your host would try searching all of these domain names when you look for a host name. Finally, a word about record types. So how are the records stored in the DNS server? We know that it stores IP to host names. That's known as A records. Storing IPv6 to host names is known as quad A records. Mapping one name to another name is called CNAME records. For example, you may have multiple aliases for the same application, like a food delivery service may also be reached at eat or hungry. That's where a CNAME record is used, name-to-name mapping. There are many more, but that's all we're going to look at for now. Now, ping may not always be the right tool to test DNS resolution. There are a few other tools as well, such as NSLOOKUP. You can use NSLOOKUP to query a host name from a DNS server. But remember, NSLOOKUP does not consider the entries in the local etc host file. So if you add an entry into the local etc host file for your web application, and if you try to do an NSLOOKUP for that web application, it is not going to find it. The entry for your web application has to be present in your DNS server. NSLOOKUP only queries the DNS server. The same goes with dig. Dig is another useful tool to test DNS name resolution. It returns more details in a similar form as is stored on the server. In the upcoming practice exercises section, you will practice viewing, configuring, and troubleshooting DNS in a lab environment on actual systems through some fun and challenging exercises. Well, that's it for this lecture, and in the next lecture, we look at how to set up an actual DNS server on a system where we will use CoreDNS as our DNS solution. Well, thank you so much for watching, and don't forget to subscribe to my channel for more videos like this.